Well, hi, this is Bob Amundson, and I'd like to welcome everybody to Chapter 1 of Statistics 252. I'm sure everybody knows we're using the 9th edition of Elementary Statistics, a step-by-step approach by Alan Blumen. I've been teaching this class since the year 2000, and this is a really good book, and it has a really good accompanying student solution manual also. So I believe this will really make our class go as nicely as possible in terms of the heavy use of examples in the text, and then the backup with the solution key. And of course, I'm sure you'll find my eLives helpful also. What I plan on doing, especially for Chapter 1 and 2, these are kind of introductory chapters, so I'm going to hit the high points. But when we get to Chapter 3, we're going to be dealing with much more numerical information and have a chance to use some new formulas and new information. But Chapter 1 and 2 sort of get us going. So I may repeat myself or overlap here and there on this first chapter just to try to get us going, but I always assume that the class members are doing a close read of the chapter itself. I'm not going to speak to everything in Chapter 1 because most of it's just straightforward reading with a few new definitions. But as I said, when we get to Chapter 3 and then through on out, I will be doing very detailed working of examples and working of explaining theory, and also working select homework problems to help class members with the new material. Anyway, we're on page 2, and they just talk a little bit about a definition of statistics. And they tell us it's the science of conducting studies to collect, organize, summarize, analyze, and draw conclusions from data. Just so you know, our first 3 chapters are going to deal with something called descriptive statistics, which I'll speak to in a minute, and then our chapters 4 through 8, those chapters 4 and 5 deal with probability, and then chapters, actually a little bit of 6 deals with probability also. But it's 7 and 8 where we actually get into making inferences or using something called the bell curve, although our book calls it the standard normal distribution. And we'll be using that in some other statistical tables to make predictions or inferences from data groups. So something else, I'm over on page 3 now, and remember, I'm just trying to hit the high points of this introductory material. They talk about a variable, which I'm sure class members are very familiar with because Math 105 is one of the prerequisites for this class. And they tell us it's a characteristic or an attribute that can assume different values. Well, you know, in your mathematical background, you've probably had stuff like you've used a variable, you've solved for a variable, like 3x minus 1 equals 11, and we add 1 to both sides and get 3x equals 12, or solving, we'd get x equals 4. Well, we really don't do a lot of solving for variables. I don't think there's more than maybe 2, 3 at the most occasions in our class where we solve for a variable like x. Most of the things we're going to do involve using a formula and plugging in the correct numbers. Anyway, just to give you an idea, we're going to be more interested in doing something or using something called random variables. I'm using a new Surface Pro 3 tablet, and it's going to take me a while. I'm kind of on a learning curve with regard to writing and using it. But when we're talking about random variables, we let x equal like 0, 1, 2, etc. And what we're going to do is we're going to make a little table or something, and the x will be our random variable. This is all happening in chapter 5 and 6, I believe. But then each one of these is going to have like a probability. Maybe the x in this case stands for the number of sales that a salesperson over the history of their career, they've kept records, and maybe on a given day for their product they know there's a 25% chance they won't make any sale, or there's a 50% chance that they'll make one sale, or a 25% chance they'll make 2 sales. So from this variable, from these using x as a random variable here, we're going to find out that there's a way to find the overall probability of x, or something called the expectation of x, by plugging into some formula. And what I'm trying to get at here is this particular example doesn't have anything to do with chapter 1 right now, but I'm trying to show the direction we're going to go with regard to variables in our class. We're going to use most likely, or in most cases, random variables, and we're going to use it to make some predictions or expectations, not unlike the little example I've just shown here. Okay, well, here's a couple of things that are really important, and I'm glad they're showing right now. They tell us that a population consists of all subjects, human or otherwise, that are being studied. And then they tell us that a sample is a group of subjects selected from the population. The idea in statistics is it's impossible to gather all subjects. And when I say that, I'm talking about maybe all the people that have high blood pressure in our country. It's impossible to get all of them and at one time in one place and make some observations. So what we would normally do, and I'm grossly simplifying here, let's say get 1,000 people with high blood pressure and then do a particular test on those 1,000 people, and from that particular information, if there's a statistical or meaningful difference in the results, apply that to the general population. So samples are very important when we're talking about in statistics, and sampling is sort of the heart and soul of the class. But whenever we're dealing with the population and we're talking about the number of that population, we use a capital N. And if we're talking about a sample from the population, we use this, the N stands for the number again. This is what we use for sample. And there's some other ideas like this that we'll be seeing very shortly. For example, we have the Greek letter mu, which is the mean. That would be like if you added your 4 test scores up and divided by 4, that would give you your average or mean value for the test. But this would be for whenever we're dealing with a population. We're going to see this real shortly anyway. But if we're dealing with a sample from a population and we want to find the mean, we use something called X bar. The bar refers to the line above that. And this would be for a sample mean. So it's good. There's other symbols that we're going to get to also, like standard deviation for a population and a sample. But those will come nicely in chapter 3. But anyway, we're seeing some things here that will be helpful for right now and in the future. And I'm going to read you the definition first. This is at the bottom of page 3. The definition for descriptive statistics. It consists of the collection, organization, summarization, and presentation of data. In Chapter 2, we're going to learn how to make something called a histogram, which is sort of a fancy name for a bar graph. And I'm just sketching with my new tablet here. I'm sure everybody's seen a bar graph before, except in statistics we call it a histogram. And there's some other graphs that we'll be learning, important graphs that we'll be learning in Chapter 2 also that are based off the histogram. And then in Chapter 3, in other words, this would be how we present the data. Okay, one way to present data, organize it in a table or a chart or a graph. And then in Chapter 3, we're going to start looking for some measures of central tendency, and we're going to look at the spread of the data and so forth. And to do that, we're going to need to learn some terms like mean, median, mode, standard deviation, and so forth. So, as I said before, Chapter 1 to 3 basically deal with descriptive statistics. And then from Chapter 4 to Chapter 8, we're going to be learning, we're going to lay the groundwork for, in the earlier chapters, 4, 5, and 6, for probability. And the probabilities will lead us into making inferences for our concluding chapters, Chapter 7 and 8. Okay, well, anyway, and again, you'll be doing a close read of this. I'm just trying to hit the high points. They tell us that inferential statistics consist of generalizing from samples to population, which I mentioned just a little earlier, performing estimations and hypotheses tests, determining relationships among variables, and making predictions. And by the way, we're going to see, more than anything, we're going to see this bell curve, or standard normal distribution. And when we get to Chapter 6, we're going to take this bell curve apart and learn all of its features. And this will help us in Chapter 7 and 8 with making predictions. So now we know that there's a couple of, two main types of statistics. And we know that we're going, the point of the class is to get to inferential statistics and hypothesis testing. And again, the book does a really good job of laying those things out. Some other things I wanted to just hit the high points on, I'm over on page 6 now, is we have some variables and types of data. This is worth looking at because we usually in statistics we're interested in particularly a couple of types of variables or sets of data, and that's going to come more over on page 8 and 9. But let's look at their definitions first for variables. Let's say when we're talking about a qualitative variable. And remember, we're setting the groundwork for classifying things. And they tell us that qualitative variables are variables that have distinct categories according to some characteristic or attribute. In other words, male, female would be a qualitative variable. And they also tell us that things like religious preference would be a qualitative variable. And they also tell us geographic locations. Those basically are qualities of some item or some behavior or population. And then, in other words, qualitative variables are based on the actual quality of the variable itself. And then they tell us quantitative, you can see quantify there. And those are variables that can be counted or measured. And that's the one that we deal with. We'll be dealing with most often. So you may recall when we're talking about just counting something, and this is really important. Remember, when we count something, we normally start off at 0. This was, we use the counting numbers. I'll put 3 dots on there to show that goes on out forever. This is actually the set of natural numbers, or sometimes called the counting numbers. In other words, it doesn't make any sense. Let's say that we're counting the cars in the parking lot of your particular college. It doesn't make any sense to have a negative answer or a decimal. Cars come in units of 1 at a time. So If somebody said, how many cars out in the parking lot? Well, if it was empty, it would be 0, and maybe at 2 in the afternoon, there might be 112 cars out there. So this is called, what we're talking about now is a discrete variable. That's the next definition down. Variables that can be counted. Okay, and this will be an important part of our class, counting variables for some particular questions. But then we also have something, variables that can be measured, and those are continuous variables. Just hope I don't mess anything up writing. Okay, and we're normally talking about measurements. Okay, and then the first thing that we get when we talk about this, you can actually count some things, by the way, in terms of variables. But when we're talking about continuous variables, we're going to usually do some measuring. And measuring the closeness or the accuracy or the extent of your measurement depends on the measuring implement that you're using. In other words, if we're on a bathroom scale, here's 150 and here's 151, and normally what we would do is if the arrow or the pointer or whatever is more than halfway, and remember, we don't have gradations in between 150 and 151 in those bathroom scales. So if it's closer to the 151, we just say, yeah, the weight is 151. But remember also that there, if you go into the chemistry lab, they have scales that can measure out to the hundredths place, the thousandths place, etc., more and more measurements. So technically speaking, you could measure something out to the 10,000th place or the 100,000th place or theoretically the millionth place. Okay, and when we were trying to show something like that on a number line, and where they're going with continuous variables is, let's say that we know that when we're talking about, let's say we're talking about an English measure of between 2 feet and 3 feet. Well, we know that that could be broken down on a yardstick to maybe into 32 parts, with 30 seconds or so forth. But, if you were using a more precise measuring instrument, you could say that the interval between 2 and 3 would be continuous because there's an infinite number of measurements between 2 feet and 3 feet. There could be a measurement of 2.6579 feet. Okay, and it all depends on the actual tool that you're using. So because every possible fraction and decimal would be filled in between 2 and 3, this is what we mean when we say continuous. And normally things that we measure are continuous. So they give us some examples up here, or somewhere close by here. Right above that little table they give us on the bottom of page 6, they tell us that continuous variables consume an infinite number of values between any two specific values, like 2 feet and 3 feet, and they're obtained by some sort of measurement. And of course they would include fractions and decimals, and certainly irrational numbers also. So, and then they give us some examples here. They tell us that temperature, and I'll just peek up to the next page a little bit, and they tell us things like length, that could be height, by the way, or weight, and age, etc. In other words, age is basically time. We know that we can break a second into millionths, or seconds can be measured to the millionths of a second, and theoretically even further than that. So these are things that would be continuous. these are measurements that would be continuous. Okay, so once we get an idea of the very important difference between continuous variables and discrete variables, and you can look at the little table at the bottom of page 6, they kind of break it down. Then we can get into something very important when we're talking, I'm down at the table 1-1 in the middle of page 7. And this is really important. I want to remind everybody, if somebody told us to take a number like 1.4 and round it off to the ones place, we would see that that 4 is, we normally round up when the place is 5 or larger. So 1.4 would just round off to 1. If I would have given you 1.7 and asked you to round that off to the ones place, then this, of course, would round off to 2, because 0.7 or 7 is above 5, is 5 or bigger. So, in other words, we can round off to different decimal places, and we do that by taking the decimal place in question. In other words, if we want to round to the ones place, we look at the value in the number in the tens place, and if it's 5 or bigger, we add 1. But if it's less than 5, we drop it and just stay with the number that we're dealing with. In other words, 1.4 rounds off to 1, but 1.7 rounds off to 2. Okay, well, for our purposes right now, we just want to learn how to set some boundaries for what some measurements mean in terms of a scale, okay, or in terms of somebody has done some measurements in table 1.1, which says recorded values and boundaries, but all of this is going to come back and help us in chapter 2 when we use these boundaries to help make some bar graphs and some other types of graphs. So this is probably one of the more important things in this chapter, as I said, most of it is just some new definitions and ways of thinking about some new material. So what I'm going to do is I'm actually going to work table 1.1 and explain how they get those values. And I'll start off by grabbing a new page here. So remember, it's assumed that we're in table 1.1 where it says length, and it says 15 centimeters. Now, what does, if you measured 15 centimeters, basically this measurement ends at the one place here. And here's my technique for doing it. There's several others. But what I like to do is I like to take 15 and I will take and put a 0 there, a 0.0, because our last place, or our measurement was rounded or assumed to the ones place. Okay, so what I do is I write 15.0 because that's the next place, and that's the tenth place. So then what I do is I add and subtract 0.5. Now, what that does, when you add 0.5 to, when you subtract 0.5 from 15.0, you get 14.5. And when you add 0.5 to 15.0, you get 15.5. So a measurement of 15 centimeters, remember, we don't know what particular device whoever gave us this measurement used, but we know that it was correct to the ones place, so there would have been rounding at the tenth place, is what's assumed here. So that means that the measurement could, the boundary of that measurement would fall in between 14.5 up to 15.5. And very important, I'm going to graph this, 14.5 would be closed, but 15.5 would be open. So if we, and this is continuous, of course, because we're talking about a length. Okay, so any number, that interval set up there would be any number between 14.5 continuous all the way up to, but not including 15.5, would be in that particular interval. Remember, a 15.5 would round off to 16. Okay, all we have to worry about right now, or concern ourselves with, is how do they get those numbers for the boundaries. Okay, how about the next one? There is a temperature of 86 degrees Fahrenheit. Well, again, this measurement has been assumed to be rounded off at the ones place, so I'm going to write it as 86.0 because that's the next place value where they would have rounded to. And then again, like the other one, I'm going to add and subtract. This is the 10th place, by the way. That's the next place over. And I'll add and subtract 0.5 again. Okay, and when I subtract 0.5 from 86, I get 85.5. And when I add 0.5 to 86, I get 86.5. So the boundaries implied by a temperature, somebody measured the thermometer, looked at thermometer, of a measurement of temperature of 86 degrees, is assumed to have a boundary between 85.5 all the way up to, but not including, 86.5. Okay, so let's go do the other two because those deal with another place. How about a time of 0.43 seconds? Okay, well, in this particular measurement, we have been given a value to the hundredths place, and the next place would be the thousandths place. So I'm going to stick my an extra 0 on there, and what I'm going to be doing is adding and subtracting 0.005. In other words, I'll be subtracting 5 thousandths from 0.43 or 0.430, and I'll be adding 0.005 or 5 thousandths. And when I do that, I get 0.4, well, I'll subtract it first, 0.425 to 0.435. Let's do that again here. Okay, they gave us that measurement to the hundredths place. I stuck a 0 on there because the rounding would have been assumed to be done at the thousandths place. And so I added 0.005 and I subtracted 0.005. And again, you can see that on the table. Okay, the last one is the mass there, and it's 1.6 grams. Okay, so that's a measurement that has been made to the tenths place. So the rounding would have been taken place. The rounding would have been taken place at the hundredths place. So I'm going to stick on 0 at the hundredths place, and I'm going to add. I'm both going to add and subtract 0.05. So plus or minus 0.05. And that would give me 1.55 to 1.65 as an interval. Grams, of course. Should always put the units on there. And if I wanted to sketch that continuous, because there's an infinite number of masses in between 1.55 and 1.65. This would be open at 1.55, excuse me, closed at 1.55 and open at 1.65, and that would be our boundaries. I may have said class boundaries because that's what's happening in the next chapter. For right now, I should just use the term boundaries, and we'll be done with it. See how you do on example 1.3 at the bottom of page 7 there. Okay, well, the next material, the next over on page 8, I'm just going to read these and leave it to you to take a look at it. And this is pretty much just by definition. But they tell us that we have 4 different types of measurements. We have nominal, ordinal, interval, and ratio level of measurements. And the ones that we're most concerned with in our class are the interval levels and the ratio levels. And I'll just give you a couple examples of each one, but again, remember you'll be doing a close reading of this. They tell us that the nominal levels just classifies things into mutually exclusive categories, and no order or ranking can be put on them. Things like male, female, religion, zip codes, and so forth, somebody's political affiliation, those are hard to quantify, although we can quantify them by counting, let's say, the number of Republicans or Democrats in a room, but we don't usually do any measurements there. And then they tell us that we have the ordinal level of measurement, which classifies data into categories that can be ranked, but there's no precise differences between the ranks. Now, what they mean by that is, like, say, we know, for example, we have the grades A, B, C, D, and F. Well, if you get an A, everybody knows what that means, but one person could have an average of, let's say, 90.2%, and in most classes that would be an A, but another class member could come up with an average of 99%. They would both get that same A, but obviously, or from what we've seen, one had a much higher average than the other one, but they both would end up with the same grade on the transcript. So that's a good example of ordinal level data, and they give some other examples also. And then they tell us that we have the interval level of measurement, and that ranks data. Precise differences do exist, but there isn't a meaningful zero. Okay, so as an example of that, they use IQ scores, and they tell us that everybody knows something. An IQ score of 0 doesn't make any sense, okay, in the way that we're defining these levels of measurement here. Another deal is like when we're talking about a temperature, for example, of 0 degrees Fahrenheit, that doesn't mean the absence of heat, which temperature or molecular movement, which is part of the definition of temperature. There is still heat there. The 0 degrees would be considered an interval level. In other words, it's not a meaningful 0. Now, the last one that we're going to talk about, the ratio level of measurement, has all the characteristics of the interval level, but it has a true 0. Okay? And we can make ratios of it. In other words, when we're talking about the ratio level, let's say that we have a child that's 3 feet tall and an adult that's 6 feet tall. We can take and make a ratio of 6 feet over 3 feet, which would turn out to be 2 over 1, or we could write it in ratio terms as 2 to 1. Okay? And in ratio level of measurement, we do have a true 0. Okay? And we'll look at all that stuff as we get through other chapters. So what I'd like you to do is just read carefully over pages 8 and 9, and you will see what we're dealing with there in terms of the examples from each type of data, and you'll also see, you'll be able to relate their examples, and they ask you to classify some different variables. Okay, section 1.3, I'm going to leave that to you. That is just straightforward reading. If this was a psychological statistics class, we would be doing much more sampling, and it's good that we're going to learn about the different types of sampling and how they're used. But in our class, when you get to chapters 7 and 8, somebody will have gone out and already got the data for us. We don't have any questions or assignments where we have to go out and gather our data. Although you will certainly know how to do that and be able to work numbers on that data by the end of the class. But we don't do that as part of our class. But you will be expected to carefully read over section 1 and 3 and then answer some questions in the homework on that. Well, the last thing I wanted to just touch the high points on was over on page 18, and that is on experimental design. I think most of us have heard the term double-blind study, and again, this is not a major part of our class. We will have the results of studies at our fingertips, but as I said before, we don't go out and get the results or design the experiments and do the tallying and so forth. We will only take the data, organize it, and make inferences from it. But you might notice that they talk on page 18 now about, in section 1.4, experimental design. We have a couple of types of studies, and in an observational study, they tell us that the researcher merely observes. They do not get into the study itself, and they don't try to affect the study by any participation. They strictly observe. And, for just an off-the-top of my head example of that, let's just say that you posted yourself by a stop sign. Most likely you'd want to be somewhat out of sight, but let's say you just sat there for an hour and tallied up the number of people that actually came to a full stop, or actually sort of blew through the stop sign, or did what's called a California stop, kind of rolled through it or whatever. You would not be directly participating, standing there, intimidating the drivers, or in any way reacting with the drivers. You'd just be there as an observer. And again, that's called an observational study. Then they tell us a little further down the page, in an experimental study, that one of the variables is manipulated, and then you try to find out how that manipulation influences other variables. I guess if we went back to the red light example, if you were standing there in some type of an official uniform, I'm sure that would have a big effect on the people as they drove through or drove up to the stop sign. If your presence there, it may have indicated that you were recording some type of behavior. Anyway, they have plenty of other examples there, but what we do in an experimental study, and they give us an example of how they had a couple of groups. We'll just call it like Group A and Group B. And in Group A, they separated the two groups, and they asked the different group, or they had two different approaches to the groups, and the groups were asked to do some sit-ups. And one of the groups was just told to do your best over a period of time, and they weren't really coached or given any specific instructions. So this, I guess we'll call A is just no instructions or no coaching. And in Group B was given some coaching or some instructions. Okay, and then what they found out, and again, I'm not going to read this to you, but what they found out is the group that was not given any specific instructions or no coaching or encouragement did not do as well over the period of time as, let's say, Group B, which was given some instructions or some encouragement. So what we basically, in this case, what we did is we manipulated the instructions, and we'll put a name with that up on the top of page 19. We have a couple of ways to name variables. Remember from your algebra career, when we're dealing with an XY pair, the X is called the independent variable. In other words, we choose values of X and we plug them in to some formula, and the Y value that comes out is called the dependent variable, because the Y value depends on what X value we stuck into the formula. I'm just trying to use the simplest examples possible here. Well, they tell us that the independent variable in an experimental study is the one that's being manipulated by the researcher. And they tell us that the independent variable is also called the explanatory variable, and that the resultant variable, that's our y value, or dependent variable, is the outcome variable. Okay, so in other words, some type of manipulation, if we want to think about it in terms of the x variable or the independent variable, you have a couple of different groups, and you treat one of the groups differently than the other group, and then you look to see what the outcome was. And they talk about a treatment group and a control group on page 19. Recall, I'm just trying to hit the high points here again. And I believe the example they used was, they go back to the sit-up study, where the independent variable would have been the coaching that they gave to that group, and or the encouragement, asking them to do better. Okay, and then they did find out afterwards that they got more sit-ups were done. Okay, and then the last thing that I wanted to talk about, and again, this is just background reading information, is they tell us that it's possible in a study like this, and again, this is more an experimental design where you try to minimize or eliminate what's called a confounding variable. And they tell us at the bottom of page 19 that a confounding variable is one that influences the dependent or outcome variable, but was not separated from the independent variable in the study. So they use the example where their subjects are put on an exercise program, and maybe the researchers didn't know that people on the exercise program had somehow changed their diet. And they tell us that their overall health improved, but since there was a confounding variable of a diet change, or at least that possibility existed, that might have influenced the overall study. So just be aware that a confounding variable is something that can affect the results, and we're always trying to, when studies are set up, confounding variables, we try to minimize confounding variables. Well, I think that's enough of the high points in Chapter 1. From your reading and the selected homework problems I've given, I'm sure that'll be enough to give us a good start in the class. So I will be back shortly with some thoughts on Chapter 2, Section 2.1. Thank you.